As often happens when we introduce new notation, there is a specific type of root for which we have special notation. The root with index 2 is something we look at very frequently, and we use it often enough that it has a special name and a special notation. The square root is the root of index 2. That is, f of x is written as just the square root of x. Notice there's no index shown. That's the function such that its inverse is x squared with its domain restricted to non-negative numbers. So in other words, the square root of x is the non-negative number so that the square root of x squared is x. Again, we have no index shown in the radical. If there's no index shown, it's invisibly 2. Now, why does this get special notation? And part of it is that we use the square root more often than we use other roots. But the main reason that this has special notation is historical. Historically, the idea of square roots predates the other roots, and I don't mean by a couple of hours. I mean by several thousand years. So the square root has this geometric reality. It represents the side of a square with a given area. So if I take the square root of 25, that's the length of a square, of the side of a square with an area of 25. The other radical functions generalize this to higher powers, but there's no real geometric reality to that. For example, the cube root, irrational cube roots are what's geometrically called unconstructible, right? Cube roots are much more unpleasant than square roots are. So it's not so much that we have this general notion of roots, but then we have the special notation for the square root. It's more, we have this notion of a square root that we've had for thousands of years. And then much more recently, we've generalized that to say, well, I guess I can undo any power, not just the second power. We work with square roots just like we work with any other roots. So for example, we can find square roots using trial and error, right? The square root of 16, that's saying what number to the second power gives me 16, right? So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. Ah, that's the one. Saying 4 squared is 16 is the same as saying the square root of 16 is 4. What about 25? Well, I've already tried 1, 2, 3, 4. Those were too small. Let's try 5 squared. Oh, that's 25, which is the same as saying the square root of 25 is 5. Square root of negative 81? I don't think there's any such thing, right? If we square a positive number, we get a positive number. If we square a negative number, we also get a positive number. Square root of negative 81 is undefined. We're restricting ourselves again to the real numbers here. Okay. What about 400? That's going to be a big square root. I think though, my last digit here is a 0. If I'm going to multiply some things together, they'd better both have last digit 0. So I'm going to maybe try 10 squared is 100. That's not it. 20 squared? Oh, there we go. That's 400. So the square root of 400 is 20. Negative 49, if I take the square root of negative 49, Again, there's no real number that I can square and get negative 41. So the square root of negative 49 is also undefined. So square roots we treat just like any other even root. It's just we don't write in the index for historical reasons.